Welcome to video 14, 3.9 differentials. Today we're going to talk about approximating different values using differentials or tangent line approximations. So the first thing we're going to look at is some information on the right here. Then we'll look at our diagram and kind of dissect it before we get into some examples. So tangent line approximation is simply y is equal to f of x plus f prime of c times x minus c. This is really just a point-slope form of an equation with the slope is f prime at some point c, and we're passing through the point c comma f of c. So if you really wanted to rewrite that into point slope, it would look like that in the pink. So differentials, let's talk about those. Let's let y be f of x, and it represents a function that is differentiable on an open interval containing x. The differential of x, which we call dx, is any non-zero real number. The differential of y, denoted dy, is the following. So we could say dy is equal to f prime of c times dx, or delta y equals f of c plus delta x. So this is the actual thing that we're trying to find. And this is minus f of c, which is our measured value. So we'll see what that looks like in just a second. Then there's some error that we're going to talk about, error propagation, all right, where we're talking about delta y, just similar to up above. And we can rewrite delta y as similar to dy, and we'll talk about that in our explanation with our graph. And the last example we're going to talk about is this relative error, or also known as percent error. So let's look at this diagram here that might help us kind of dissect those formulas. So suppose we are having this graph f of x, or y is equal to f of x, and I have my tangent line at point C. Okay, at point C, but I want to be able to evaluate f of x using this tangent line. Okay, so I'm going to use this tangent line to approximate. So say I want to find f of x, I'm going to evaluate it on this tangent line, and if it's really close, I'm going to say it's good enough to this actual value. Okay, so my tangent line is at C. All right, and so we've got f of c, okay, that's where that comes from. And my actual value that I want to find is this x value, and that leads me to a y value. So we talk about this delta x, which is the difference between x and c, and we have this delta y, which is the difference between y and f of c. So if we let delta x be x minus c and delta y be y minus f of c, then we can kind of manipulate things. So we could say y is equal to f prime, that's our slope, times delta x plus f of c. So that's just using our point slope formula. If we subtract f of c, we have y minus f of c equals f prime of c times delta x. Again, delta x is the x minus c. And then another way we could denote y minus f of c, we said, was delta y. So delta y equals f prime of c times delta x. So if x is small, the second point moves closer to that first point, right? So x moves closer to c if x is small, okay? So that means these two are really close to each other, which also means that delta y, which we could say is like dy, while delta x is approximately dx. So what we have is dy is really f prime of c times dx, and delta y is really y minus f of c. This is our ending value. This is our starting value on our curve. Okay, so let's get into an example and see how things go. Okay, so let's use differentials to approximate the square root of 9.2. So what I'm going to do is I'm going to graph y is equal to the square root of x. X is really what I want is 9.2, right? The square root of 9.2. But I'm going to use the point when c equals 9 because I can take the square root of 9 pretty easily. Okay, well, very easily. So I'm going to let my tangent line be my tangent line at c equals 9, okay? And I'm going to use this tangent line to approximate when x equals 9.2. Okay, so if y is equal to the square root of x, we need to know what f prime is. So we take the derivative of the square root of x. We get 1/2 x to the negative 1/2. Delta x, remember, is x minus c, and in our case, it's 9.2 minus 9, which is 0.2. And remember, delta x is the same as dx. Okay, so now we're going to actually use our formula, that tangent line approximation, okay, to approximate the square root of 9.2. So remember our formula, y is equal to f of c plus f prime of c times x minus c. That's our delta x. So I'm just going to plug in. We know c is our 9 value. So y is really equal to f of 9 plus f prime of 9 times 9.2 minus 9, or our 0.2. Okay, so now I'm going to actually plug in. Well, we know what y is equal to. Y is equal to the square root of x. So really we have the square root of 9.2 is approximately, f of 9 is the square root of 9, plus 1/2, 9 to the negative 1/2. That's our f prime over here. And our delta x is 0.2. And now we're just going to clean it up to approximate. So when we clean this all up, we end up with the square root of 9.2 is approximately 91/30, or 3.03 repeating. In actuality, the square root of 9.2 is this guy over here, so we're actually pretty darn close using that tangent line for our approximation. Okay, so just kind of food for thought here. This tangent line approximation for f of x equals the square root of x at x equals 9. Remember, I have my tangent line is at x equals 9. This is the equation for that tangent line. We were able to find our slope, right? And at the point when x is 9, or c is 9, our y value is 3. So this is where we get that tangent line. So for x values near 9, the graph of f, which is our black graph over to the left, and g, our red graph over to the left, are really close. Okay, so any value that's close to 9, it's okay to use that tangent line approximation. It makes sense. They're close to one another. However, the further I move away from 9, my tangent line does not become very accurate to use as an approximation. Okay, let's use that concept now to use a tangent line approximation of this function, f of x equals x cubed minus 5x plus 3, near 2.1. So this is where our tangent's going to be. For near 2 comma 1. For x equals 2.1 and x equals 2.01. So we're going to use two approximations here. So let's just quickly go ahead and draw a graph, right? So here's f of x, and here's our tangent line at x equals 2. Okay, so we're going to use this tangent line to approximate when x equals 2.1 and when x equals 2.01. All right, so remember our tangent line approximation is f of c plus f prime of c times x minus c. So let's find what f of c is. So c is 2, that's where our tangent line is, okay? So f of 2 is going to be 1 when all is said and done. Taking the derivative of f, we get 3x squared minus 5. Evaluating f prime at 2, we get 7. So then our delta x for our first approximation, x minus c, is going to be 2.1 minus 2, or 0.1. So we can go ahead and plug that in to approximate f of 2.1. So we do that. F of c was 1 plus f prime of c was 7, and delta x was 0.1, and when all is said and done, we can clean it up, and we get f of 2.1 is approximately 1.7. If you were to actually plug in 2.1 into our function, you would get this value, so you would see it's very close. I want you to try evaluating f of 2.01. The only thing that's going to change is your delta x, x minus c. So go ahead, see what you get. Okay, so hopefully you got what I got, and the only thing that changed was our delta x, which was now 0.01, and you get 1.01 for the approximation of f of 2.01. The actual is this here, so you can see, again, we're pretty darn close. Now let's look at an example where we're just comparing or using our function from above and x equals 2 to compare delta y and dy for dx, or delta x is the same as dx, which is 0.01. Okay, so remember our delta y function is f of c plus delta x minus f of c, where c is our 2 value, or x, and delta x was given to us at 0.01. So really, we're taking delta y is equal to f of 2.01, the actual value of it, minus what we're measuring it from, f of 2. Okay, so we're using the actual from what we said up above, all right, for f of 2.01, not our approximation, and we're subtracting 1. So we get delta y is this guy right here. So what's dy? Well, remember, dy is that f prime times dx. So f prime of c, or f prime of 2, was 7. We found that up above. And then they're giving us the delta x, or sorry, dx. And so we get dy is 0.07. So you can see they are pretty close to one another. Now we're going to look at an example that uses propagated error, possible propagated error. And in this one, we're looking at computing the volume of a tank. So let's suppose the radius and height of a storage tank and the shape of a right circular cylinder are 60 inches and 240 inches respectively. So that's our diagram down there. The possible error in each measurement is 1/2 inch, meaning the delta r is between -1/2 and +1/2. All right, that rate at which it's that change. And same with delta h, it's between -1/2 and +1/2. Okay. So we're going to use differentials to approximate the possible propagated error in computing the volume. So this is where we're just finding the derivative. We're using dy is equal to f prime times dx. So since we're talking volume, we need our volume of a right circular cylinder. Okay, so that's pi r squared h. We're given r is 60, h is 240, dr, or delta r, is ±1/2, and dh is ±1/2. So we need to use implicit differentiation here, all right? So one in terms of r, one in terms of h. So we take the derivative of v, we get dv. Now with respect to r, we take the derivative, we move that power out front, 2 pi r, h is like a constant here, and then we have to have dr in there. Now using that product rule, plus pi r squared, taking the derivative of h, we're just left with dh. So now we can go ahead and plug everything in, right? We know r is 60, h is 240, dr is ±1/2, and dh is ±1/2. So when all is said and done and cleaned up nicely, we get ±16,200 pi inches cubed. So the possible propagated error in terms of the volume is ±16,200 pi inches cubed. It seems like a lot, right? Now let's move on and find the approximate percent error. So on the front of these notes, I gave you that formula, the percent error, and it's simply the derivative over the volume, derivative of the volume over the volume, or the rate of change of the volume over the actual volume, or our propagated error over the actual, and it's the absolute value of that. So the first thing we need to do is we need to compute the actual volume of this cylinder. So we go ahead, pi r squared h, we plug in, and here's our actual volume of that cylinder. So now to figure out the percent error, all we have to do is use what we found above, that propagated error, and divide it by the actual volume. And of course, we're taking the absolute value. That means we don't have to worry about the plus or minus here. And we get really, there's an error of 1.875%. So it doesn't seem that big compared to this number up in part A. All right, if you have any questions, make sure you ask those in class next time we see each other.